So some more on ARMA processes. As we discussed, so ARMA processes are finite order systems or rational systems. So it has ARMA stands for Auto Regressive Moving Average, and so this is the regression part. In other words, the whatever you are looking for, x of n, depends on p samples from its past, and also a moving average of something else. So notice the symbols. Here, of course, this only goes from 1 through p because xm is all. So xm depends on previous p values, and it's a moving average of some other process. So because this is, if all the bi's are equal, that's a weighted average of, including, look at here, current value of wi, Wm, and the previous values. Of course, the current value is here for x is on this side. So it's a finite order system because this is not infinity, this is not infinity. So this is generally referred as ARMA PQ. So remember, it's a stochastic process because this is a stochastic process. So xn is also a stochastic process. So it makes sense to, let's say everything is zero mean. So it makes sense to look at look in terms of its n is also good, right? In terms of its autocorrelation function Rk, which is expected value of xn, I'm going to write this as in this manner, xn minus k. So of course I'm defining it as t1 minus t2 if this is Rk, right? This is t1, this is t1 minus t2 is Rk. And this minus sign is just a convention. You can have plus sign here, or in other words, minus ai, you define it as ai tilde or something. So in any case, this is going to be sigma ai. Some of this we went through it, expected value of xn minus I, xin minus k, right, star, plus summation bi or wn minus I, xn minus k star. So this is going. So this gives us Rk is minus summation ai. So t1 minus t2. So that's Rk minus I plus summation bi. So if you look at this term, this W goes from Wn minus 1 up to Wn minus Q. So in general, this may not be 0, right? Especially if n is small, there could be some overlap. Because look at here, xn depends on previous Q values of W. So you can see if k is beyond q plus 1, then if k is beyond q plus 1, then this will be from if you, or just here, which W, so this will depend on this W will depend on W n minus K. Look at here. Here, because of this, whatever is this value, it goes Q values further, which is what I have written. So whatever is this value, n minus K, it goes beyond Q values further. So this will go up to n minus K minus Q. So if I put, look at here, if you put K equal to Q minus 1, you can see that this set and this set will have no overlap. That's what we want, right? So if you put here K, even if you put equal to Q plus 1, see this only goes up to n minus Q, then this will be n minus Q minus 1, n minus Q minus 2, etc., right? So these two will be, because if you assume, of course we are assuming that Wn samples are uncorrelated with each other, zero mean uncorrelated. That's generally the, you can assume Gaussian. If you assume Gaussian, this also becomes Gaussian. But generally the assumption is this is a noise process which is at least uncorrelated. So these samples are, so my point is you can clearly see that this will be zero. Clearly you can say that when K is greater than or equal to Q plus 1. So that's the key equation I want to start with. So now you see, because of this minus sign, if you want, I can bring it to one side, or I'm going to write it like this. And I'm going to do a few manipulations and show you so of course so you can clearly see that you may say we don't know Q, this is the other way, right? K greater than Q plus 1. See, Q is a finite number, so even if you don't know, if you go far enough on K, this equation will be automatically true from somewhere onwards. So that statement is, this statement is generally, is true if K is large enough. And you have infinite set of equations. So you can see from those infinite set of equations, somehow some rank conditions should pop out so that we can figure out the P. In the, generally the big problem here is you don't know P and Q. You don't know the model order. That's the biggest problem. You collect some data and you want to fit a model of this form, a finite system model, where the question is what is, so the two questions. Maybe in one case the data actually came from a system like this, ARMA system, and you only have access to this. So from this data you estimate the RKs, covariances. These covariances you can see, begin to see some, obey some equations. So from these equations we need to figure out P and Q. So I'm going to, and the second thing is, you have some data. We don't know whether it came from ARMA system or not. But we want to fit it into a best model for using a finite model order like this. Then we would like to figure out what will be the best value of P and K. So that's a more difficult problem. That is not what I'm going to talk about. I'm going to talk about the first problem. If the data came from an ARMA system, and if you, generally you only have access to RKs, but then you can estimate the covariances like this. For example, sigma xn minus k star k equal to, what K is the data samples. And if you use m data samples, so K goes from 1 through m, then you divide by whatever number of data samples you use, divide that by that, that would be an estimate to this, right? And so this is an estimate, not an exact value, but or otherwise, the ideal problem is you are given the covariances of this process, find me the P and Q. So in any case, we have this equation.
So you don't care about the AIs? Like,
Yeah, of course. I mean, the whole point is, I'm saying in the first step is to find P and Q. Then, of course, you find the AIs and BIs, right? Yeah, right. So if I use these equations, start writing from for k equal to q plus 1, etc., you can write it in this form, right? So I take P equations. So k equal to, look at here, k equal to q plus 1, I equal to 1. So it will start with RQ, right? I is increasing, so this is going to decrease, right? So you get an idea, I'll write a couple more equations.
The negative sign, right?
Yeah?
There's a negative sign.
There is a negative sign because you take the RK to the other side, right? You mean here, right? Yeah. So I use q plus 1, this is q plus 2, etc. I use P equations. Remember, look at here, unknowns are 1 through P. So this I want to make it to a square matrix. So this will be P by P. So first equation, second equation. First equation is 0, 1, so P minus 1, P equations. So you'll get this. So 1, 2, up to P equations. So you can see here, if you, from here, so you can argue that because the system has a unique A1 through AP, this matrix has to be full rank. And then you take the inverse, you can solve for A1 through AP. But the question is, you don't know what P is, right? You know, this is okay if you, so let's proceed. So let me call this matrix to be RPQ. So you notice how the notation is. You start with the Q, and then the size is P by P. This matrix is P by P, okay? So that's the definition of RPQ. So let me look at RP plus 1, Q plus 1. So that's going to be RQ plus 1, RQ, etc., RQ minus P. So what I have done is I've taken, look at what I've done. I've taken this row to the other side, and so then this minus, because of that, it will become plus. So I put a 1 here, so you get this to be equal to 0. So from here, you get this equation. So notice that all I wanted to say as before, that this is according to the previous notation, we have just increased everything by 1 by, we start with the q plus 1, but I increased one more row. This is now p plus 1 by p plus 1. So anybody, what is the property of this matrix now? Why not? What? It is the same equation. I just brought this up to this, and I added one more row, right? Because going this way, I have plenty of equations, right, all the way to infinity. So I added one more row just to make it p plus 1 by p plus 1. So my question is, what can you say about, because a matrix multiplied by a non-zero vector equal to 0 means?
Less than p plus 1 rank.
Huh?
Less than.
So this matrix is not full rank, and this matrix is full rank, because this matrix is full rank because if this matrix is singular, because we have a unique solution for A1 through AP. Why do you know? Because that's where we start with, right? So you can argue that way. We have A1 through AP are unknown, but they are unique. Yes?
Why are they unique?
Because I give you a system. Remember, this Xn satisfies a unique, so we start with an ARMA process. So Xn will have this structure. So all the A's cannot be 0. If all the A's are 0, Xn equal to only the B's, right? So the A's have a fixed, unique values, right? That's good. So those unique values, because all these are all of them are not zeros. Because this is not a zero vector, this matrix has to be full rank, right? I mean, so anyway, so you can see from here it is, this matrix is, so using the same argument, if you go, you should be able to see that this matrix is also singular, right? So how do you write this matrix? You start with the q plus I, then you go down subtracting 1 for p plus k, because the size is p plus k by p plus k. So the next entry will be rq plus I minus 1, and the last entry here would be, I'm just taking motivation from this matrix to define the, so the number of rows and number of columns are p plus k, okay? So I start with the q plus I, then reduce 1. So this is first column, second column. So the last column will be q, what is it? Anybody? Yes? And similarly, the next one, of course, will start with rq plus 2. Then this will be rq plus I. So the last diagonal entry will be q plus I. This will be rq plus I plus 1. And this entry here will be q plus I plus p plus k minus 1 I have, right? Now you can, a couple of ways you can do, but you can quickly see that if you, remember we already, look at the basic equations here. So if this k is beyond q plus 1, then it's a linear combination of the previous p values. You see that? So you can see from here, that's another way. So this is already, because what is the size of this matrix? Anyone? Right, P plus 1, right? So if you take this row, this column, last column, how many more columns are here beyond? This is P plus 1, the column. So how many columns are here? P columns. So you can see that this is a linear combination of the previous P columns. Look at here, right? So the last column, you can see that this last column is a linear combination of the previous columns. If you have a matrix of that form, that's singular, right? You don't see it, or what's your problem?
I'm still not convinced that that's a square matrix.
Well,
It's not a square matrix.
see, this is a square matrix, right? Yes? All right, you bring this row here, that's what we have. Bring this column here, right?
Yes.
So that will start from RQ plus 1.
And ends at RQ.
Okay, so this will be R, you're right, RQ plus a P, and this will be one more, right? Then I'm just putting in whatever is the next, remember there are infinite set of equations. I just make it P plus 1 by P plus 1 by bringing in one more equation.
So this is not directly from that. The next equation.
The last equation is from here. All the equations are from here. No, I mean, whatever is the pattern here, you just increase it one more, right?
Okay, but why would it be 0 when combined with these 8?
From here. So remember, that's where you get all this stuff. Why would this be?
So you're setting k equal
To the next, the next one, whatever is the value. Here it is q plus p. Yeah, you can see here. I've used up to q plus p here. So use q plus p plus 1 here. So then this will be square. But another way to see it here is that this column, you can see here itself, this column is a linear combination of the previous p column. So this matrix is singular. Same argument goes here. So long as for any k and any I, for these columns are is a linear combination of the previous p columns. So what is the property? So the property is that for an ARMA PQ system, a rank of R of p plus k, q plus I, this matrix is not rank. Yeah, rank is actually equal to p for k positive, I positive, because it's the same argument here. Look, at all these matrices are evolution from here. This matrix has got full rank. Its size is p. This matrix is, you just added one more row and that is singular. And this matrix is already part of it. So the rank cannot decrease. You can use it Sylvester's inequality or whatever, right? So, okay, so this is the, as I said, so that should be, remember, so RP, a rank of RPQ is P. Because it's P by P matrix, full rank. But if you either increase, if you create the same structure beyond that, it's going to be singular, or the rank stays the same. So let me look at RPP, and I want, but here you may say one issue, in using this as a test is we need to know what the value of Q is, right? But usually we don't know Q. So I want to get over that problem. So let me define it doesn't have to be, but usually, because we know the transfer function corresponding to this system is BZ over AZ, and that's going to be so the usual assumption is the denominator has a higher degree than the numerator. It doesn't have to be, but let's assume that's the case. So if P is greater than equal to Q, then from here we would get rank of so you'll get this identity, right? See, this is true for any value of y. P minus Q is positive. So if I plug it in here, P minus Q plus K, you get and let me just write this matrix. So R of P comma P plus K comma P plus K is going to be right? So this matrix is going to be rank P for K So that is true for any K, strictly positive, that's going to be P. So let me pick up RPP. So let me put K equal to 0. So remember, that's only true for K strictly positive. So if I put K equal to 0, this will be And let me, J is this matrix with unitary along the other diagonal. So if I multiply this R by, so this is just going to flip the rows on the right side, then I have, this will become R1 through RP, R2, etc., RP plus 1, etc., RP, etc., R2P minus 1. So H is for Hankel, because this is a Hankel matrix. Why do you Hankel has got all these diagonals exactly the same. So this is a classic result. Remember, this is full rank because it has got a P linearly independent. So if you multiply by on the right or left, it doesn't matter. By a full rank matrix, rank doesn't change. So whatever is the rank of this is the same as this. And you can see, what we could see from here is all these. So now you can use the same argument. Any of this also, so HP plus 1 would be going the other way. HP plus K would be Hankel matrix, but starting from R1, R2, etc., RP plus K, R2, R3, etc., RP plus K plus 1. And or P plus K, etc. So you can see again, if these rows are a linear combination of the previous rows if K is greater than 0. So the classic result is for a ARMA system, so you see you can find out P without knowing P. So I hope you saw the, so here again the same argument. If you, this column is a linear combination of the previous P columns. If I have enough, so long as the matrix size is more than P. So you can start with K equal to 1, 2, 3, etc. Because from that same equation we had here. And this one you cannot write this, look at here, you cannot write this as a linear combination because there are no P previous columns, there are only P minus 1 columns. And consequently, so the rank of this is the same as this one. Yes, that you can see from here because first of all, this is a subset, right? HP is here, right? That's HP. So this is true. So look at the argument. This is true, but here what I am saying is, if I make this index large enough, then the rank will be rank will be the same as the rank of HP, which will be P. So if you plot the, so one way to determine is you plot the determinant of HK. So initially it will have some value, but somewhere it is going to drop. So that will give you P as a hypothesis testing, right? So you start with a small, where is HP? HK is here. So you start with small values of HK, take their determinant, and if you keep plotting it, at some point it is going to be, so because of the noise consideration, etc., even if the determinant doesn't exactly become 0, from a finite value, you will see it will drop down to significantly small values. And so then you have to make a decision as to what's the value of P. Knowing P, you go back to these equations, whatever. You can even go here, those equations itself, because there are infinite number of equations. So in fact, this multiplied by AP equal to the A vector equal to minus of the RPs from there. So you can find out the AKs, the denominator.
We are given R beforehand, right? We are given R beforehand.
So that's the, usually you only have data. From the data you need to estimate the R's, right? So the same equations, if you start these same equations, so what was the equation? RK, what is it? Plus sigma AI. The first equation we had, what was it? Equal to 0, right? So if you use, this is for k greater than q plus 1, right? So if you take it equal to k equal to p minus 1 onwards, then you will get this equation. So either you can use this or you can use, the advantage here is you don't need to know P, you don't need to know Q. The only assumption is Q is greater than P. So I will start using this equation k equal to P minus 1 onwards. P is already known, right? So you just go and use the corresponding equations. So you will get the you can solve for the denominator, right? So this is a very famous identity. This goes back to, I think, just this, the last line. That's all enough. Everything is summarized here. Which is the same, another way to say the same thing is this way. So remember what is HK. So the theorem is the following. So this is the Hankel matrix generated from the covariances. So the theorem is so this is certainly true, right? For a large enough k, look at the last line, large enough k, the determinant of HK is, the HK becomes singular. So the question is, where it changes from non-singular to singular, that's where you will get the P. Or a little more, so this is the cheapest way of saying things. A little more costlier is here. So this is rank of HK stays the same beyond a certain stage. So that stage where it changes is because rank of HP is P, but every Hankel matrix beyond HP is also rank P. So that will give you the, so you have thousands of tests. You can find the determinant of HP plus 1, P plus 2, all of them has to be consistently 0. Then that is already telling you that you are dealing with a rational system or a finite order process. This is the key In other words, there is only so much movement within the R case within a rational system. So there are, the key here is, look at here, here are p parameters, but there are an infinite set of equations here. These equations are infinite because it is true for all values of k large enough or beyond q plus 1. So it doesn't matter what q is, because for the first problem, which is finding the denominator, you can push these equations, you can start digging into the equations from beyond a stage where you know that q is before that. So you see, interestingly, we don't need a q to find out the denominator. Now, knowing the numerator and knowing the denominator, now this way you can completely find the denominator, right? So a of z, if you want an expression, if you want to write this up, you can write it like this, right? Right, so we'll consider this, or AP, whatever. But AP through A1 is here. So if I call this matrix to be D, DP, not DP, what is it? That's a Hankel matrix, right? So that is HP minus 1. Then this is going to be 1 minus this vector HP minus 1 inverse, then RP, etc., or 2P minus 1. So this, I don't know whether you remember this. We can write this as so this may be 2P. I used a matrix identity, which I'll explain to you. So if you want, you can also put it in this compact form. In any case, the APs, the A1 through APs are known, so you can solve for the denominator. Then in principle, how it goes is, knowing the denominator, you can multiply by the denominator here so that you get a purely numerator piece, and that's easy to, then the coefficients are easy to find out using a number of different ways. All right, so this is, I just wanted to come to this key identity. That's what I wanted to give you. This is identity, I think, is due to Kronecker. So for rational systems, so it's a simple statement. For rational systems, the covariances created from the Hankel matrix has the property that the Hankel matrices all are singular beyond a certain stage. That stage will give you the degree of the denominator. So you can see what plays the key role is the degree of the denominator is important. Now another way is to find out the numerator is, you can flip the system. In other words, from here you create that's one way, an inverse process where the role of B and A are reversed. and then you work with that inverse process to find out the numerator coefficients.
But then we don't have P greater than Q.
Yeah, then but remember, you already know P, right? The denominator. So then that means you know the Q there.
Do you know a bound on the Q?
No. We already found the exact value of P. So when you flip it in the inverse problem, the numerator degree is now known. So remember, so this is known there, right? Because this will be, for that new system, it will be beyond, so P, that P is known. So then you just use the exact number of, the value of P to find out the.
So then the question is only finding BIs, right?
Yeah, so instead of A, you will be solving for the BIs here, right? BIs here, and that's all you want, right?